there are three phases of learning electronics. So first you learn how to, in theory, design your circuit. Then you really have to design your circuit. And the final phase is when you power up your circuit, it goes in blue smoke. And the same, I believe, is true for hardware security. First you learn how to design your secure system. Then you really try to design it. And finally you realize it's not secure. So in my talk, I will present evaluation of hardware security in Intel Max 10 FPGAs, and then I will discuss challenges in implementation of some attack methods and summarize certain threats that come out of implementation of those attacks, and then we'll talk about future and conclude. So hardware security is important because it protects the data and intellectual property. It prevents various attacks on services. It teaches you how to implement countermeasures against unknown attacks, and it educates hardware engineers. So the hardware security is about finding flaws and fixing them, and for that you have to evaluate existing systems and improve them. And there are lots of challenges for hardware security. You always have to face new attack technologies. You have to work with modern fabrication processes, which are now down to 7 nanometers. And you have to develop countermeasures through understanding of flaws. And you also ideally would like to predict new attack methods. So why security of Max 10 FPGA is important? Because this FPGA was designed for security applications. It doesn't have external flash memory with configuration bitstream. Everything is on the die. They also offer AES encryption of the bitstream. And there are 3 security fuses to protect information from readback, to encrypt, to only allow to run the encrypted bitstream, and there's also a fuse that can disable the JTAG. And it's obviously positioned as a secure device, and also you can't find any documentation on JTAG commands and security features. It's a suitable candidate to mitigate modification attacks. If you remember, a year ago there was a big noise about some backdoors, not backdoors, some Trojans found on the Supermicro server motherboards, which were compromised by changing the contents of SPI flash, and that kind of device can prevent these attacks. There are certain pros in the Max 10 because it has small size and low cost, and it has 2 configuration images on the internal flash, so you can run safe update and you can easily recover in case of any errors. But some downsides is still SRAM FPGA, so it's prone to soft errors. And the keys are stored in flash memory, and for many years it was proved that flash memory is not the best way to store the keys. So with the design process, first you compile your design into soft file, and that file can only be loaded into SRAM of the FPGA. In order to program the flash, you have to convert this file into POF file. And then you can add some security to the POF file, so you can encrypt the contents of the file and add AES key to the configuration, and you can also set some security fuses. So without any security activated in this particular device, you have some system memory that is always read protected, and it can only be written once after the erase operation. And there's a user flash memory that stores some user data. Without protection can be read and written. There's a configuration memory with also full access. And there is some shadow memory at the end, which is factory programmed. You can read it, but you can never write into it. And there are 3 security fuses, as I mentioned. Verify protect fuse makes the device read protected from JTAG, but still you can program soft file, and that means you can program Trojan design into SRAM and then run it and read out the memory. If you activate encrypted POF only fuse, it blocks the direct access to SRAM, so you can no longer upload soft file into the FPGA, but it has no effect on JTAG. So you can access the device through the JTAG and read out all the data. And the third fuse is JTAG security. It blocks any access through the JTAG. So it's high security level available on this device. So this obvious security flaw, the manufacturer doesn't tell you that you have to activate both verify, protect, and encrypted POF fuses to actually protect your design from being read out. And that could cause some problems in the security. Another security feature is that this bitstream configuration is protected against modification. So in soft file, there's a 16-byte number unique for each design, and there's also CRC at the end, and obviously the way they calculate those numbers is proprietary. So any modification to the configuration will cause the device not to boot. And also the POF file that can be easily modified because it's just a flash image. But if you try to boot modified image, then you won't succeed. If you try to set the fuses, then you will immediately see the result in the POF file. So if you set verify protect fuse, it sets certain area in the memory, in this case the address 030, and there's also a few bits in the configuration memory. If you encrypt the bit stream, then they put the AES key into the system memory, and also they scramble the key, but they scramble it by changing the positions of nibbles. So you see that 0 goes into that place, 1 goes into this place, and so on. So you can easily unscramble it. And also it sets the same sequence of bytes at a different address. For encrypted POF fuse, this sequence of bytes goes into another address, and also a few bits set in the higher memory. And the similar things happens with secure JTAG fuse. So from that you can assume that when the device boots, it reads out the contents of the memory, finds this magic sequence, and then makes a decision what fuse is activated. You can also compile a staple file from POF file, and that is high-level programming usually used by the end user for JTAG access. And they also obfuscated staple files, so instead of using some meaningful variable names, they use just numbers. But still, you can find all the instruction and data register commands, and you can use print command to print out the contents of the registers and variables as they executed. So with the attack methods, I decided to use all three: invasive, semi-invasive, and non-invasive attacks. So with invasive attacks, which are high cost and require long setup time, I only went to evaluate the size of the flash memory, the complexity of the FPGA logic and JTAG logic to estimate the attack time. For semi-invasive attacks, I performed optical fault injection, and for non-invasive attacks, which are usually low cost and are used by many attackers because they're easily to transfer between attack teams, I looked at undocumented JTAGs commands for any backdoors. I looked at data remnants, power analysis, electromagnetic analysis, and various glitching attacks. So with invasive attacks, which are most dangerous because they can potentially give you full access to the internal device features, unfortunately, those attacks are usually so expensive that only well-funded organizations can perform them. They require highly skilled and knowledgeable attackers, and they're also time-consuming. So for my evaluation, I only used backside polishing down to polysilicon layer. At this point, I was able to put the device under the microscope and look at the cell structures. And the fabrication process is stated by the manufacturer as 55 nanometers. So obviously at that level of integration, you will need an electron microscope to resolve any components. But still, the optical microscope, you can estimate the complexity of JTAG logic, which I estimated as 60,000 gates. So that means it would take several months to reverse engineer this device and find out any flaws in the JTAG logic. I also looked at the flash memory, and surprisingly, the flash memory cells were quite large for 55 nanometer process, so it's about a quarter by half micron, and that means you can see individual memory cells under optical microscope. So they're about 10 times larger than compared to usual embedded flash and microcontrollers and system-on-chip devices. With invasive attacks, the other question is not only how dangerous they are for the real device, but also how dangerous is to perform those attacks, because they could be dangerous also for the person who implement them. And that the reason for that is because most invasive attacks involve chemistry, and the chemistry is science of, does anyone remember what is science of? And then you might try to remember what you were taught in the school. Well, the chemistry is the science of two things. It's poisons and explosives, because it comes from alchemistry. So deprocessing and also semiconductor fabrication process, they have both. Because for deprocessing, hydrofluoric acid is used to remove silicon oxide and also for selective action of silicon. This is a very poisonous compound. And also for cleaning, they use piranha solution, which is a mixture of hydrogen peroxide and sulfuric acid. It can explode on its own, but also they use solvents for cleaning. If you mix those two things together, they will explode immediately. And also as to the poisons, all chemicals are poisonous. There's no exceptions. And that's why at the university you're taught to always wear protective clothes, put gloves on your hands, sign all sorts of forms, and get some sophisticated training. And the reason for that is that there's a parameter to compare various chemicals, how poisonous they are. The parameter is called LD50, and that means that with 50% probability, how much chemicals do you need to for half of the animals to be killed. They usually test it on rats, and that is set the amount of chemicals per kilogram of weight. And you can see that for hydrofluoric acid, you need only a few milliliters to kill someone. And for hydrogen peroxide, it's a bit larger, but still it's a relatively low amount. And the same is for sulfuric acid. But also solvents, they're also quite dangerous, so probably not more than 100 milliliters could cause severe harm to you. But obviously, in real life, you come across various chemicals when you do some cleaning at home. So, for example, if you have some problems with your sink, it gets blocked, you go to a shop and you buy some chemicals to clear the pipes of your sink. And for that, they either use sulfuric acid, which is quite dangerous, or you can go and buy some alkalines. And those alkalines are either sodium or potassium hydroxide, and you can see the poisonous level is very close to the hydrofluoric acid, and hardly you will wear all the chemical protective clothes and put gloves and other things. But also you drive cars, and petrol and diesel are at the same level of danger as solvents used in fabrication process. Not only that, but also you go to party and you drink alcohol, and it's the same level as petrol or acetone. But not only that, but you go and you go to have some lunch or dinner, and you use salt, and the salt is as dangerous as other general chemicals used in semiconductor fabrication process. So, and you never wear gloves to put some salt in your food. And if you think there are some safe chemicals, then water also has some limits. So it's only 10 times less dangerous than alcohol. So next time you dilute beer, think twice. Now I move to semi-invasive attacks. So for experimental setup, I need to access the surface of the chip, and for that I go from the back side. So I mechanically open up the package of the chip and I put it under the microscope. And also for that I build a special adapter so I can insert the chip. And also I built a special test board that was communicating with the chip via JTAG and also was controlling the laser. And so then I use an infrared laser with 50 milliwatt power, and I scan the full surface of the chip, the 100 micrometer steps, trying to find the sensitive locations that could change the contents of the security fuse. And as a result, you see there's this very small area where I was able to switch the security fuse from protected state to unprotected state. So next I zoomed into that area, so it's about 1000 by 1000 microns, and then I scanned it with a higher resolution, and during that process I set the verify protect fuse, and the laser was at the same level, and you can see there are many places in the flash memory where you can inject the fault with the laser, and then that would cause the security protection fuse to be disabled. And the same experiment I ran for JTAG security fuse, the highest level of security in this device. And again, you can see that there are many spots in the flash memory where you can inject the fault and switch off the fuse and then get full access to the contents of the device. So again, semi-invasive attacks, they are quite dangerous because they deal with the lasers. Oh, so there's another part. I also run the experiments for timing analysis, trying to figure out the optimal time of the fault injection. So for that, I was sending the laser before the TCK pulse of the JTAG, and also after the TCK pulse and before the TCK pulse. And you can see if the pulse is delayed after TCK, there's no change in the result. So you always unlock device at the same time. But if you terminate the pulse before TCK, then you have to do it very close to the TCK. So obviously the effect of the pulse is only sensed by the device during the rise age of the TCK. So now a few words about the danger of semi-invasive attacks. So because they work with the lasers, they are dangerous, and many lasers are not visible, so it's very difficult to tell when the laser will hit your eye. And also there are two classes of the lasers, 3B that can blind you, and the power is only 5 milliwatt. And remember, in my experiments, I set the laser to 50 milliwatt. And also class 4 lasers, they are more powerful. They can not only blind you, but also cause some burns. But at the same time, lasers are used in medicine. They used to cut tissues and for medical treatment. They used in ophthalmology for eye surgery. And it's mainly the non-collimated lasers which represent the biggest threat. If you deal with a focused beam laser, then they're mostly safe unless they hit the mirror or a white wall. But the most amazing experiments I've seen on the lasers was when I was shown a class 4 laser, the infrared 1064 YAC laser that was, so the device was quite small, and the beam was focused at about 20-25 centimeter. And when the beam was fired, you can see in the air just a big boom, just a big flash. And you can hardly imagine where these devices are used. It was demonstrated by ophthalmology people. And if some people might remember that when you look at the white wall, you sometimes see small particles that are flying in front of your eye, and you cannot get rid of them when you blink. And this is because these are small pieces of tissue that are located in the liquid between your cornea of your eye and the pocket that holds the crystal. So over time, they usually disappear, but in old age people, these particles are quite large and they could stay there for ages. So those surgeons, they had these devices with infrared laser collimated with red laser, and they focusing on those particles inside your eye, and then pressing the button that caused this class 4 laser to shoot on these particles. So now about non-invasive attacks. So first I looked at undocumented JTAG commands because in the hope that I will find some backdoors. And I looked at user guides and BSDL files which are used to describe the JTAG boundary scan and JTAG commands, and I also converted POV file into STAPL files, trying to find all the commands that can be used. And I also scanned the JTAG interface for the length of command and data registers, and I also tried to observe power consumption for detecting active commands. So I did manage to find some commands which were not documented, but none of those commands are found to be useful for getting access to the data on the chip. And another challenge with non-invasive attacks is that if you have the JTAG security fuse set, then you can no longer run anything through the JTAG. Also, I looked at data remnants. This is the residual data left after you perform the erase operation. And obviously, when you do full chip erase, you also reset all the fuses. So the idea is to terminate the chip erase operation at the right time to cause the fuses to be disabled, but the data to be preserved. And you do this by terminating the power supply of the chip. And that, of course, does not work if the JTAG security fuse is activated, but it did allow me to extract about 97% of the information from the chip. So for running the JTAG commands, I used the universal programmer because you can not only run the chip read operations, but also you can modify the POV file if any data you write into the chip. And I also had a test board where I put the chip with some power supply and power analysis connections. I also tried to override the memory because surprisingly, even the security fuses are set. You can still write into the memory. You can change any bit of information from 1 to 0 in the user and in the configuration flash. So if there's some kind of a checksums of signatures running inside, then obviously you can work out the contents of the memory by going bit by bit. However, timing attack will not work because they read the data in large chunks. For small devices, 64 bits. So you will need a large number of the devices to figure out the time when the corrupted memory was detected, because you can see in the device response when once the boot process hit corrupted memory, it immediately stops, and you can see it. It has two logic I/O signals that determine the start of the boot process and the end of the boot process, so you can figure out when this memory was corrupted. But power analysis can reveal a single bit change in the memory, and also if the encryption is used, then obviously single bit change will cause the change in the large number of bits, and that could be easily detected through the power analysis. And again, the same problem, you need JTAG to be enabled. So the power analysis, I just used a resistor in one of the power supply line. I was only interested in the core power supply because that's where the logic is supplied from. And then it's a very simple setup. You just record the power trace and you compare two traces with different settings. So this is the power trace of the boot process. So you can see that first the device reads some internal configurations, and then it starts the boot process, and then these are two logic signals I mentioned. So this is the start of the boot process, and this is the end of the boot process. So the device actually tells you when the boot process is finished and whether it has any errors. And also from the power trace, you can extract valuable timing parameters that will be needed for fault injection attacks. You can also do averaging across multiple power traces because this device does not have any countermeasures against power analysis. You can compare traces with different AES keys. You can compare traces between normal and corrupted flash. And you can see that once the flash is corrupted, the boot process immediately terminates. And you can see this in the power trace. And you can compare the last corrupted data in the device, and then single bit change will cause the different decrypted data to be processed by the device, and you can clearly see whether this single bit change causes any difference or not. So you can extract the contents of the device if the device was encrypted. Doesn't matter whether you had this verify, protect, and encrypted for fuses set, because you can still write into the device, although you cannot read. And the biggest challenge with that kind of the device is because the configuration is stored on the embedded flash, so you cannot easily run it like the conventional FPGAs that run from external flash. So modifying the data takes a much longer time. So I also tried electromagnetic emission analysis by observing leakage using a small magnetic coil and H probes. And the advantage is this probe can be positioned at different places across the device. And also there's no need to remove the chip or insert any resistor, so you don't have to modify the circuit board. And usually this analysis requires preamplifiers because the signal is much weaker compared to power analysis. But I didn't find any advantage of using these methods because signal-to-noise ratio was much worse than the power analysis. And also I found that contribution of the internal clock was so high that it was several orders of magnitude larger than any useful signal. You can get some improvement from positioning the sensor, but still because I was performing it on a fully packaged device, because with at least 0.6 millimeter thick packaging that did not help. I also tried power glitching with the device. So for that, I was injecting glitches into the core power supply, and I tested both single power supply devices that had internal regulator that took external 3.3 volt and turned them into 1.2 volt core power supply. And with dual supply devices, it's easier because they are supplied from external 1.2 volt. And as expected, dual supply devices are easier to glitch because you can immediately send the glitch to the core power supply, and the glitch on the power line looks like this. So, and also you have to insert it at the right time. And I ran it for both devices at different voltages and different length of the pulse, and you can see the result here. So for these devices are usually supplied from 3.3 volts, so I had to go down to 1.5 volt to inject any faults. And the number of faults is still quite small because the device has more than 2 million bits of flash, and also only a few hundred of thousand bits were corrupted. For dual supply device, I had to go to about half of the power supply with even less, but I was more successful in changing the contents of data from the device. So these attacks are quite powerful and useful, but you have to be careful with injecting the glitch, because if the glitch goes too low, the device will reboot. And the last non-invasive experiment that I ran was fault injection using electromagnetic pulse. And that kind of attack was very promising because there are many publications on how to inject faults. And the setup was described in many publications, but usually what I found difficult is the parameters of the pulse. So what you use is you use fast changing magnetic field to inject eddy current inside the device, and that causes some voltages to rise in the input of the logic and changes the contents of the registers or memory. But I went into difficulties trying to reproduce some parameters, because usually if you read papers and publications on that kind of attacks, they only specify the duration of the pulse and the voltage of the pulse. And here you come across the first challenge is what hardware to use in order to get this pulse. So you can either use off-the-shelf equipment, like a high-voltage pulse generator, that you will connect to the coil through probably quite a long leads, or you can use signal generator with high voltage amplifiers, and again you have a long cable to the coil. But you will have wires introduce some parasitic resistance, inductance, and capacitance, so the pulse voltage will be reduced. You will get a pulse fronts not very fast, and you will introduce unnecessary oscillations. So it will be very difficult to reproduce precise pulses using standard off-the-shelf equipment. So custom design could benefit from better control and of the pulse parameters. And also the custom board could be brought closer to the device under test. But here comes the challenge number 2, is how to control the duration of the pulse. The coil that is used for electromagnetic pulse injection has certain inductivity, and the inductivity determines the way how you control the voltage across it. So there's an equation that tells that the voltage on inductivity is determined by the change of the current across it, and L is the inductivity of your coil. So if you aim to have a fixed voltage on your coil, then you will end up with your current constantly rising inside the coil. For an average 10-wind coil, which is used for most experiments, you will end up with about 100 nanohenry inductivity. And that means that if you try to create a 100-volt pulse, you will end up with the current that ramps at about 1 amp per nanosecond. So in 10 nanosecond time, you will have 10 amps, and if you try to create a 100 nanosecond pulse, you will have to feed 100 amp into your coil. So it will be very difficult to produce that kind of pulse. Either your power supply will run out of steam, or your switch that controls the coil will be unable to hold that high current. Now, you also have challenge number 3, that is maintaining the pulse parameters. So you can try to use a capacitor to hold the energy necessary for the coil, because once you charge the capacitor, you can store a certain charge, and that can be used to supply the coil with the current. So with the capacitor, the things are much easier. Once you charged it, it holds the voltage. But there comes another problem. You cannot create an infinitely long pulse with the coil, because at some point the coil will be saturated, and no longer the current will grow linearly inside the coil, because at that point the coil will turn into a resistor, and in fact very small resistor, about 0.1 ohm. So maintaining voltage across the coil will be prohibitively hard. You will have basically 3 possible options. Either your power supply goes belly up, because the current that you will need to send for 100-volt pulse across this coil will be about 1000 amp, or that means 100 kilowatt power supply, or your transistor will become too stressed and start smoking, because even if the very small channel resistors of hundreds of ohm, it still be 10 kilowatt, a big kettle, or your coil becomes too happy and will start firework if you manage to get that current through it. Now there's another challenge. once you started everything, how are you going to stop it? So the coil accumulates the energy in the form of magnetic field. Once you stop supplying the energy, the coil wants to get rid of that energy. It has to go somewhere, and another problem, it has to go very quickly, much quicker than you supplied the energy. And that creates what's called flyback voltage across the coil. So you expect the pulse to be like this, but you end up with very high voltage spike. And if you think that that spike will not affect your circuit, then I try to reproduce that experiment. So this is the voltage across the coil, and I put the H probe next to the coil, and you can see that on the probe, the magnetic field exactly replicates the shape of the signal with some filtering. So obviously on your device, not only your initial pulse will have effect, but the most effect you will feel from this flyback voltage. And also the 50 volt pulse, it could easily go to 500 volts. And that high voltage could be damaging for your equipment or pulse generator. It could be damaging to transistor, and it could also damage insulation and cause damage to other devices in your circuit. So how do you get rid of that unwanted pulse? So if you want to reproduce the experiments clearly and you want to have full control over the pulse, you might think you will somehow remove that flyback voltage pulse. So that comes to the last challenge in how to get rid of the unwanted flyback pulse. You can try to modify the pulse generation circuit, and you can then test the result in real circuit. So the obvious solution, you might be told, at the university is you use also so-called flyback diode. So when you switch on the relays or motors, they always recommend you to put this diode to get rid of these pulses. And also, for verifying those ideas, I built a test circuit, and I put some voltage dividers before feeding them into the oscilloscope. So this is 1 to 10 high voltage dividers, because you cannot feed 500 volts into the oscilloscope. And then the circuit is very small, so there's a capacitor that holds the charge, the voltage on the coil, the small coil under test, and the transistor that switches that coil. And you can see that the pulse is, the flyback voltage is higher than the initial pulse, and this is the power supply on the coil. The next question is, do you think that circuit will work? That kind of diode will work for that circuit? Well, for that, you have to ask some experts or some assistant for research to tell you how the diode actually works. And the best one is to find someone who knows the nature. So before finding suitable diodes, you have to learn how it works in the so-called forward recovery voltage, because that's what we actually do. We apply voltage in the reverse bias to the diode, and then we go back into the conductive mode. So how does the diode work? And also you have to think about the diode that is that can withstand very high voltage and reasonably high current. So the natural principle of the diode operation can be explained in 4 pictures. So first, you put the diode under stress, applying high reverse voltage. You see? Then, once the voltage goes to 0, it gets relaxed. What happens next to the diode? Well, the next diode goes into sleep mode. Before and after a certain time, it's ready to operate. Well, the question is how long the diode is going to sleep. Well, for average rectifying diode, that's about 100 nanoseconds. But if we look at our pulse, this is 10 nanometer per division. The whole pulse will end in 10 nanosecond time. That means it's very difficult to find such a diode. So I had to look into so-called super fast rectifying diodes and also ultra fast rectifying diodes. Most of them are low voltage devices with relatively low current. So the best one I managed to find are these devices, but even them, they cannot go to very high voltage, except the last one. It can hold 400 volts. And another problem that I found is the manufacturers do not usually supply specify the parameter of forward recovery voltage. They usually specify only reverse recovery voltage, the opposite operation of the diode from conductive state into blocking state, because that's what's important for switching power supplies. And then out of these diodes, the best one, this DFLU 1400, as you can see, it was active only after 4 nanoseconds. So it's still, the flyback voltage was about 150 volts. So this is 50 volt pulse, and then originally it was going to 400 volts. Now it goes only to 200 volts. It's still not enough. So next, I looked at other types of the diodes, because those diodes were PN junction diodes, and usually they are associated with a high recovery time because of the recombination. So if you go for Schottky diodes, which are primary carrier diodes, they're supposed to be faster, but again, most of them are low voltage devices. Very few can withstand voltage above 200 volts. The best I found was these two, and they had about 3 nanosecond recovery time, which is again only just enough to put the reverse voltage, to block the reverse voltage at about 200 volts. And then I also looked at other semiconductor materials, because silicon is not the only material available for diodes. It's also gallium arsenicum, gallium nitride, silicon carbide. Gallium nitride, I wasn't able to find any because they're very rare. Gallium arsenicum, the low voltage, the only one I was able to find is this one. It's 40 volt maximum reverse voltage. Silicon carbide, quite promising, high voltage, high temperature, fast rectifying diodes. So I tested all of them, and still you can see that the best time was about 3 nanoseconds. So still, they're still not very good. And then I came across the data sheet on Infineon diode. For this particular diode, datasheet says some marketing good news that it's a revolutionary new material. It has no reverse recovery, no forward recovery. So that should be something that will solve our problem. But then, further in the datasheet, you find that this the junction charge is about 4 nanocoulomb, so that's the charge that is accumulated inside the diode, and also it has a certain capacitance of the junction. So obviously you have to remove that charge before the diode starts conducting, and 4 nanocoulomb is somewhat about 25 billions of electrons, and that's enough to store 1 gigabit of information in iPhone. So it's obviously not something you can remove in no time. So also what is no time, presumably is something non-detectable, but by modern oscilloscopes, which can detect as short as 1 picosecond pulse change. Also, any attempt to remove 4 nanocoulomb within 1 picosecond will require very high current, because the current is defined as the charge traveling per time. And also, silicon carbide diodes are vertical devices with about 0.5 millimeter working area, so you have to remove that charge from the working area of the diode. So any attempts to remove those electrons within distance of 0.5 millimeter within 1 picosecond will require very high speed, actually higher than the speed of light. And also, the diode doesn't have a zero capacitance, so you will have to recharge the capacitance of the diode. So definitely, this magic device is worth looking at. So I bought this device from a distributor, and I put it into tests. And as you imagine, no magic has happened. So I don't know who was writing those so-called final data sheets on those devices, but the recovery time was close to other silicon carbide diodes, about 3 to 4 nanosecond time, and still not good enough to get completely rid of this flyback voltage. So that means that the best approach to inject fault into devices using electromagnetic pulse is to actually use this pulse rather than trying to get rid of it. But so in my experiments, I was just relying on characterizing the height of and length of this pulse rather than trying to generate my own pulse. So here are the results of the pulse glitching. So I was disrupting device operation to cause some faults. So I tested both single supply devices and dual supply devices as in power glitching. And both single and dual supply devices behaved equally because I was injecting fault directly into the device. So it doesn't matter whether they had the on-chip voltage regulator or they were supplied from the external power. And here's the number of faults depending on the height of the flyback pulse and the duration of the initial pulse. And you can see that at high voltages, the number of faults injected in flash grows, and the same is with dual supply devices, and at about from 200 volts above, and you can inject faults in the devices. And also it's much easier to inject electromagnetic faults compared to power glitching because you don't have to cut any power supply lines. It's easier to get closer to the device, and it can be done through the package. And again, do those attacks pose any danger to the attacker? Well, obviously, if there are high voltages involved, that could be dangerous. And also, the capacitors, they're dangerous because once charged, they can hold voltage for a very long time. You can charge the capacitor and then go for lunch or come back next day, and it will still have high voltage in it. And also, inductors are dangerous because if current through them is terminated, then the voltage surges to a few hundreds of volts, which is also dangerous. Also, electromagnetic pulse can destroy semiconductor devices, not only injecting faults, but causing permanent damage. So you have to be careful with the amplitude of the pulse you inject. And there are some limitations and the improvements that could be implemented on attacking Max 10 devices. So these devices are built with 55 nanometer process, so it's very challenging for full reverse engineering. However, the flash memory cells are quite large, and that means you can perform semi-invasive attacks and inject fault directly into the desired memory cells. However, the memory size is quite large. It's several megabits. So obviously, if you want to effectively perform attacks, you have to have very efficient methods and solutions for those devices. Also, because these devices use memory encryption, they pose additional challenges for finding keys and finding decryption algorithms, because not only they use the encryption, but also they use some obscurity, some permutations in the key bits. And also the lack of documentation on those devices make them quite challenging to perform the attacks, and especially reverse engineering. So for future work, there's obviously more research needed for successful non-invasive attacks, because these attacks are the most dangerous for the devices. They can be easily reproduced by many attackers. However, the power analysis is unlikely to help with data extraction from the flash memory. It can help with key extraction, but still you have to get the data out, which is more challenging compared to other FPGA devices with external flash storage, because once you got the key, you can decrypt the bit stream. But with on-chip memory, you also have to get the access to the memory. And with power glitching, it will require better tuning to bypass the security fuses, and the same applies with electromagnetic fault injection, because not only you have to change the contents of the memory, you have to change it at the right time. And also in terms of the research into hardware security, collaboration with the industry always helps, because it can bring new ideas and could help in testing new methods, because the funding is essential, but with proper funding, it could be possible to go beyond state of the art and develop something new. And also work in the areas of new methods for direct memory extraction, because if you have the device that stores the keys and the data in the flash memory, and if you can somehow image the memory with electron microscope or some modified electron microscopy methods, then you can easily extract the keys and then extract the contents of the memory and then decrypt it. But obviously more research and development is needed, because once you come across deep submicron devices like 55 nanometers or even 40 nanometers, you need more advanced methods. And also the research paper on this attack methods I'm planning to make available online by the end of September. And you can always look at my homepage for the latest news. So to conclude, so Intel Max 10 FPGAs can be attacked with different methods, as I demonstrated. The question is this really a problem? Because the device was not certified for high level of security. It might affect some customers, but for most of them, they might be okay with just having protection of the memory that is stored on the chip, not in the external memory. And it's not always true that the latest devices on the market have the best hardware security features, because you never know how security was implemented by the manufacturer. And there are many interesting targets for security research. But most importantly, what you have to learn from my talk is that be careful with lasers, chemicals, capacitors, and inductors, because they can bite. Yeah, thank you. I hope you enjoyed it.
I think we have time for one or two questions.
So do you want to comment a little bit on the weaknesses that you found by those new undocumented JTAG commands?
No, as I mentioned, I tried them all and they didn't help so I tried them in combinations with other memory accesses, the normal memory readout with JTAG, and then by issuing those commands, the various data, they didn't affect the readout process. So the fuses, the security fuses were still doing their job.
Okay.
So it might require reverse engineering of the JTAG logic to actually figure out how to use those commands, or maybe there are other disguised commands that help.
Thank you. Can you say something about the fuses that you came across to lock the device? What type of fuses there were, and did you try to sort of maybe circumvent those fuses at all?
If I go back, so the fuses, in the very beginning, I mentioned that the way they store the fuse is to go a long way. Yeah, here. So when you activate the fuse, you change the contents of the memory in the system area, And you see that for verify protect fuse, they write this sequence of 4 bytes. So for different fuses, the sequence is different. If you combine fuses, they both will be written. But what happens next is when device is boot, some kind of the internal state machine logic reads out this memory location. If it finds this sequence of bytes, it activates the fuse. If any bits in this sequence is incorrect, then the fuse won't be activated. So in order to inject the fault, all you need to do is to change any bit in those sequences, and then the fuse will be deactivated. So, yes, I inject the fault during the time when the boot logic reads this memory location.
Hello. Thank you for sharing this amazing research with us. I have a question about your work process and the faults that you detect. You gave us some figures about the number of faults according to the pulse shape and so on. And what are the faults you're talking about? What do you measure? And what do you consider as a fault in your setup?
So I was reading the whole memory through the JTAG. So these are faults that I injected into the flash memory of the configuration. So the on-chip configuration flash memory. So the whole memory was unprotected, and then I was able to read out the contents of the memory, and now I was comparing the original image with the image I read from the chip, and that this the number of faults in this readout.
What, those faults in the SRAM or was it the fuse?
It's in the flash, in the whole configuration flash, which is about 2 megabit, 2.5 megabit.
So it was kind of permanent until you, of course, erase.
No, they're not permanent. They only present were there because the fault was injected during the access time to the flash. Once you remove the fault, you can read the memory without any errors.
So we've run out of time, so I think other questions can be taken off stage. And we have a 25-minute tea, coffee break. We'll see you guys after that. Thank you, Dr. Sergei.
Thank you.